This last part of lesson 11, which is lesson 11D, is called the Bernoulli equation. And it looks similar to what we've been doing, except that on the right side we have y to a power, y to the nth power. So it's named after one of the famous Bernoullis. There are about three of them, James, Jacob, and Daniel. And this one was figured out by James, who was the father of Jacob and Daniel. I believe those were their names. Anyway, there are at least three famous Bernoullis. They were all great mathematicians and scientists. And James Bernoulli did his work, most of his work, in the 17th century, right at the infancy of calculus. So he figured this out in Isaac Newton's and Leibniz's lifetime. And no doubt it probably has something to do with the science or physics type of problem they were studying. Alright, well, Bernoulli figured out what to do here. He said, let's multiply this equation by 1 minus n y to the negative n. So now where did that come from? Well, the 1 minus n is a convenient constant. The main thing is that he's multiplying by y to the negative n in order to cancel this out so that we have a q to the x on the right side. But we'll see what happens. So I think rather than run through the theory of this, it would be more productive to just work a problem. So I picked number 7 on page 97. To illustrate this, we have y prime plus y equals to x y cubed. And it fits this format where n equals to 3. N equals to 3. So I'm going to multiply this equation by 1 minus 3, that's negative 2, y to the negative third power. Alright, now, like I said, the main thing is that we're canceling the y cubed over here. But the 1 minus n, or the negative 2, makes this a little more convenient for us, as it turns out. It's a convenient coefficient. And we'll see that in a second here. So if I multiply through here, I've got minus 2 y to the negative 3 y prime minus 2 y to the negative 2, because combine your exponents here, equals to negative 2x. Alright, now here's the punchline to this, why it works. This term right here is the derivative of, what is it, y to the negative 2 power. And then I have minus 2 parentheses y to the negative 2 power equals negative 2x. So let's verify that. When you take this derivative with respect to x, you'll get negative 2 y to the negative 3 times the derivative of y prime. So that works out. And now, if we let, I'm going to write it up here, because we want to save this for later reference. If I let u be equal to y to the negative 2 power, let me erase this stray mark up here. If I let it be that, then I've got the derivative of u dx, du dx minus 2u equals minus 2x. So this equation is in the form that we're accustomed to, the linear equation of first order. Except I'm using u's instead of y's. So if I solve this and then put the y's back in, we'll have it, won't we? So let's see what happens here. I need to do some erasing. The integrating factor is going to be e to the integral of negative 2 dx. Alright, so that's e to the negative 2x. So I'm going to multiply this equation by e to the negative 2x. And this gives me e to the negative 2x u prime minus 2 e to the negative 2xu equals to negative 2x e to the negative 2x. Alright, and the left side should be the derivative with respect to x of the integrating factor times my variable u. So I want to make sure, I always like to check these. So this derivative, I've got u prime times e to the negative 2x plus, because of the product rule, this derivative is e to the negative 2x times that derivative, negative 2, times u. It works out. And so I can separate this differential of e to the negative 2x times u equals minus 2x e to the negative 2x dx. Okie dokie. Now then, that right side, when I go to integrate, that right side looks kind of nasty to me. And we'll have to use integration by parts to work it. So let me go through those steps. Integration by parts. The left side is just, we cancel the differential symbol, and we get e to the negative 2x times u. But the right side, let me work this down here. Just this integral separately. So, and let's don't confuse the u I'm going to use with that u. If I let u be what? Let's let it be minus 2x. And then dv is e to the negative 2x dx. And you know what? I changed my mind here. Let me make this x. And we'll make this negative 2 e to the negative 2x dx. I think you'll see why I changed my mind here, but when you do integration by parts, you've got to split this up into two pieces. So u is this x term and dv is the remaining terms here. Alright, well, if I take the differential u, du is dx, and v would be the integral of the right side here, and that's simply going to be e to the minus 2x. Because if you go backwards, take this derivative, you have e to the minus 2x times negative 2. Do the chain rule. Alright, so remember that the integral is u times v, so that'd be x, e to the negative 2x minus the integral of v du, e to the negative 2x dx. And that would be x e to the negative 2x. And if I integrate this, I think it's going to be plus e to the negative 2x over 2. I want to check that. If I take this derivative, I keep the e to the minus 2x, I multiply by the derivative of negative 2x, which is negative 2 over 2 is negative 1. Okay, that works out. And then we'll also get the plus c in all this. Alright, so I'm going to have this term equals to the result of this integration, which is right here. So let me recopy that up there neatly for you. So we have this integral is simply e to the minus 2x times u. And then we have this integral, which we calculated down here, x e to the minus 2x plus e to the minus 2x over 2 plus a constant. Well then, let's see what to do. How about we multiply everything by 2 to get rid of this, and e to the 2x times 2 e to the 2x. That's going to eliminate most of the e terms. So I'm going to erase all this stuff down here. Multiplying through, we're going to get, the e to the minus 2x cancels e to the x, 2x in all these cases. So I end up with 2u is equal to 2x plus the 2's cancel, so plus 1, plus 2 times c is c e to the 2x. Alright, that looks a little better. Now the u is y to the negative 2, which is the same as 1 over y squared. So 2 times that is 2 over y squared equals to 2x plus 1 plus c e to the 2x. And so there we go. Let me see what form the book puts it in, and we'll see if it's right. That was number 7. So the textbook, looks like the textbook divides everything by 2. So they have 1 over y squared equals to x plus 1/2 plus e to the 2x. So c over 2 is still constant. So, oops, c. Divide c over 2, we still get c. So I have 1 over y squared equals to c e to the 2x plus x plus 1/2. That matches the textbook. So there's the Bernoulli method, and I think I'll do one more, and it's number 23. It looks pretty nasty.